Okay. All right, everyone. Thanks for joining us today. My name is Martha Lowe. I'm the Director of Education Strategy at ACMA. I'm excited to welcome you all to today's webinar. We're going to be learning about various testing methods, some testing equipment, international standards, and then we'll take a look at some future trends too. As we get started, just run through a quick housekeeping notes. We do have everyone on mute today for call quality, but we really encourage you to ask a lot of questions. So you can type those in the question box located on the right side of your screen. We're going to try to answer as many of those as possible at the end of the webinar today. This is being recorded, so you'll receive information on how to access that tomorrow afternoon. And then finally, if you are just joining, you should be able to see in the chat box 3 files that we've shared from Instron. There's a white paper and some additional resources that you can take a look at. And I will share those again right now for the people who are just joining. So you should see them popping into your chat again. All right, all 3 of them are there. So very good. So we have one more poll that I'm going to go ahead and share. And this one is, do you currently use an Instron universal testing system in your facility? Yes, no, or we use a different universal testing system. We'll take a look at those results in just a moment. So our webinar today is powered by Instron. They're a leading manufacturer of mechanical testing equipment, offering a comprehensive range of solutions for testing composite materials and components. This includes systems, accessories, and software used to perform tensile, compression, flex, shear, torsion, and impact testing. And joining us from Instron is Applications Manager Stefan Botsky. Stefan's primary focus centers on static high-force testing for composites and other high-strength material applications. Thank you for joining us today, Stefan. It looks like 71% of your audience have used Instron in the past, 15% have not, and 12% are using a different universal testing system. So this is a fantastic opportunity to change their mind.
Thank you.
All right. I will turn it over to you. Thanks for joining us today.
Yeah, thank you everybody for joining today for an introduction to mechanical testing for composites. So you can see already on the screen here many different fixtures and a testing machine, a typical testing machine for composites testing. So yeah, let's look a little bit at our agenda today. First, we're going to look at composite materials and their properties, how to determine those. Then we're going to look at an overview of composites testing, pretty big piece here. I'm going to go over various different types of testing and testing standards. Then we're going to talk a little bit about testing challenges and how to overcome those, and then integrated system solutions for composite testing, as well as some future trends. All right, so we're going to get started with the material properties. So composites are being used in many different end applications. So you can see a couple of examples up here. We got an airplane. Obviously, the trend goes to using a lot less fuel with your airplanes. So one way of doing that is using materials that are lighter, but at the same time as strong or even stronger. So composites are a good choice there for this end application. And with each plane generation from the manufacturers, the percentage of composites being used in those is ever increasing. Automotive, there's some applications there. You usually see it in like high-end application, racing cars or high-end cars, but then also there's some adoption now. For example, here you got a BMW car where the frame is made out of composite. And then another big driver for composite demand is the wind industry. The blades of windmills are made out of composite, traditionally glass fiber composites, but with the trend going towards larger blades to generate even more energy. So some of these blades are getting up to like 100 meters long. You kind of need to switch to stronger materials there, like carbon fiber. So there's glass fiber being used, but also a much greater percentage now of carbon fiber being used for the blades of the windmills. Now, looking at the materials themselves, a composite usually has 2 or more distinct faces. So, it could be made out of 2 materials, maybe even more than that. Usually you split those up into a matrix material, and the other one would be the reinforcement. So we got examples down here. common matrix materials, you would have something like a polymer. So a thermoset or a thermoplastic could make up the matrix of your composite material. Those are also the most common ones that we see from our customers that are being used for making matrix material. Other examples could be ceramic or metal, and then there's obviously also a lot of natural examples for composites, like wood would be a good example there in nature. Now, looking at the reinforcements, these can come in different forms. We can see here a couple examples down here. So it could be just particles mixed into your matrix material, here indicated by the little black dots, or it could be something like short fibers, chopped fibers, as you can see here. But really, to get like strong materials, you need something like continuous fibers. So it would be something like this here. You can see them, you can orient them in all kinds of different ways. And then these also can get stacked on top of each other to create more balanced materials. So we're going to talk today mostly about the continuous fibers. So what could those be? There's different examples. There's really endless. I mean, there's really many different types of materials that can be used there. The most common ones that we see also for like higher end materials would be obviously carbon, glass fiber, and then basalt for some special applications. But there's also a lot of natural fibers that can be used, like cocoa, hemp fibers can be used, bamboo. There's a trend going towards more natural fibers, which then, not all of those necessarily give you the same strength, but it's a lot more environmental friendly. So today's focus is going to be in this presentation on composite materials made out of polymer matrices with either carbon or glass fiber used as the reinforcement. So that's what we're going to focus on today. So moving on now to the bulk properties. Now, if you think of a traditional material like a metal or a plastic, those are isotropic materials. So that means that the properties are independent of direction. So if you think about a metal, it doesn't really matter in which direction you're going to put a load on there. It's going to have the same strength in all the different directions. Now, composites, on the other hand, are considered anisotropic, where the bulk properties vary strongly with the direction that a load, for example, is applied. So if we look at this orthotropic laminate example below here, it's going to be very strong here in direction number 1, but not so strong in direction number 2 and 3. And why is that? So if we look at this example down here, this little block, so the black dots in here, so we see here two rows of black dots, those are supposed to indicate fiber toes. So a fiber toe would be thousands of individual, let's say, carbon fiber filaments put together into a toe. So those then get like bundled together. It could be anything from like 3,000 up to, like, I've seen examples of 100,000 and above. Those get bundled together and then embedded in resin to make them, stick together. And then you surround them by a matrix material. And there's really many different ways of doing this. So in this little block here for our example, all of those fibers, you can see here the black fiber toes, and then the lines here indicating their direction. So we have continuous fibers all oriented in direction number 1. So that's also, obviously, they're the reinforcement, as we have established, right? So that's really where the material is going to be really strong. However, those continuous fibers are oriented in your composite material. So direction number 1, if we put a tensile or a compressive load on there, our material will be very strong, whereas in direction number 2 and 3, it might be dramatically weaker. So that's the big difference there between an isotropic and an anisotropic material like composites are. Now, few more things to note here. So directions number 1 and 2, that is defined as the in-plane direction, and then the direction number 3 would be the through thickness direction. So if you think of this being the thickness of your material and you start applying loads there, either compressive or tensile, that is the through thickness direction. And then in the common testing standards, so we're saying direction number 1, number 2 here, with the fiber orientation in the standards, direction number 1 would be the 0 degree fiber orientation, and 90 degrees would be the direction number 2 here in this example. So usually in the standards, that's how that's identified, with the 0 or 90 degree or other kinds of orientations. Interlaminar flexure properties are also important for composites. These are usually stacked up on top of each other with different plies. And of course, also, these are the properties of your composite materials are influenced by temperature and humidity. So they do take up humidity, And it also depends then if you're thinking about an airplane operating up in 30,000 feet, they will be in different temperatures than down on the ground, for example, right? So if you're testing your composites, you got to make sure that you also simulate the different conditions that your material, your end application needs to operate in. So you got to have them conditioned in a humidity little chamber, something like that, where they, get saturated with the right amount of humidity. And then you also need to simulate the test temperature that your material is supposed to operate in. Now, moving on to the different composites testings, what is being done? So if we're looking at something like this testing pyramid here, which it's pretty simple, generic specimens down here in the bottom, and you kind of move up in complexity here. You're actually building structures like at the end here, supposed to represent a finished airplane wing. So if we're looking down here, fiber resins, so we're gonna have those individually by themselves being tested. So the fiber tows need to get tested, the resins need to be made into coupons and being tested. And then you also combine those, which would be the next step up here. You have normal coupons, and then you also have some with holes in it. So it's already kind of indicating, okay, this is how you actually also fasten these together. Use fasteners to put those composite coupons together, maybe. So you also need to simulate that. Now, looking at the different testings that are being done. So there's tension testing. So if we're looking at the fiber at the 0 degree direction here, and we're testing in tensile, so that would be a fiber dominant property. Fibers have to carry the load in tension. And then if we have a fiber orientation of 90 degrees, then so that would be perpendicular to your tension load. And we have a matrix and a fiber matrix adhesion property there that we're testing. So how good is the matrix in holding everything together? If we're looking at compression, that is more of a matrix dominant property, which kind of depends on the stiffness and the adhesion quality of your resin that you're using, being able to prevent buckling of the fibers. So the matrix needs to make sure that those fibers, as we're compressing them together, that they don't buckle and that they stay in place and are able to carry those loads, and of course also the fixtures that are being used. We're going to look at also supposed to prevent that from happening. Shear testing is a matrix dominant property, transferring the stresses across the composite coupon that we're testing. And then if we're looking at flexure, it's a combination of all of these. So if the upper anvil is coming down on our composite coupon here, then we're going to initiate a compressive load, and the lower supports here where the specimen is resting on will introduce tension loads. And in the middle, what is happening here is going to be some shear forces being tested. And there's also a range of structural tests being done on the coupons. For example, that open hole here. So you need to do open hole tension or compression testing, because you need to find out, okay, drilling a hole into there, what does that actually do to my coupon? And then also bearing loading, because if you use a fastener in there, you need to simulate that fastener, and you need to put loads on your coupon to find out, okay, what is the maximum bearing load that this coupon can take. And then there's also more testing like compression after impact, where you're simulating the impact on your composite coupon and test it afterwards in compression to find out how much strength is actually left in my material after it has been impacted by a known force. Now, in-plane testing, in-plane tensile testing, that's what we're going to look at next. So we're in the in-plane direction, as we established before. What can that look like? So we got a little video here playing. This is a typical in-plane tensile test here with a coupon that has mostly 90 degrees fiber orientations, and you can see these really kind of explode on you. You got fibers flying around, definitely making it challenging for the testing machine, for your testing in general. Another example we have here, this is recorded with a high-speed camera at 1000 frames per second. And you can see even at that frequency of recording, it's basically impossible to really see this failure coming. It's very, very abrupt failure. This is a 100% UD material here being tested. This is going to loop one more time here. So you can see it again. It's basically instantly happening. So a lot of challenges here in with materials like this. Obviously, very spectacular breaks, but also obviously this is putting a lot of challenges for people like us when we need to test these materials. So I hope that gives you a pretty good idea of what a tensile test can look like, and also all the debris and dust that is being emitted during the test. So what are examples of in-plane tensile testing? So again, we can have specimens with a variety of layups, different orientations of the fibers. So this would be an example here on the left. All the fibers are oriented in this direction, a zero-degree coupon. This would be all the fibers directed in the 90-degree direction. And then this would be a more balanced one, which could have a variety of layups. We could have 0, 90, 45 degree all mixed together with different stacking sequences. So there's all kinds of possibilities of not just what materials to use, but then also how do we orient our reinforcements in those materials. Now these testing coupons, they can come in many different shapes and forms. Pretty typical, what is being used is, for example, tapped specimens. So tabs are what you can see here at the end of the specimen. So you have your normal coupon here, and then you have tabs bonded to the ends. Why would you want to do that? Well, tabs are there to prevent damage that the jaw faces would do to the fibers. So if you're clamping on to your specimen without tabs, you might break some of those fibers, and then your material is most likely going to fail in the jaw faces, which would be not a valid test in most testing standards. So these tabs are preventing those damages, and then they also make it a little bit easier about the gripping in general, because they can be gripped in a range of different manual or hydraulic grips with just normal serrated faces. So you don't need any special jaw faces necessarily for these tabbed specimens. Now, obviously, adding tabs, which also has to be done very, very precisely, it's going to be very time consuming for you, and it's also going to be adding costs to your testing, and it can also be very difficult. So for example, if you're using thermoplastic as your matrix material, then those usually have very low adhesion qualities. So it's not even going to be either not going to be possible or going to be very, very challenging to bond tabs to your specimens. So then you have to grip those specimens without tabs, which then again, we know there can be damage being initiated in your coupon, and it's going to be even harder to get a good break here somewhere in the gauge section. So gripping untapped thermoplastic specimens can be done with very fine patterns on your jaw faces, or you can use something like a carbide coated jaw face that can also give very, very good results. And then if we're looking at these standards up here, for example, the ISO 527-4 and 5, for example, now have recommendations regarding this approach in the latest revisions. Another in-plane tensile material that we can look at would be protruded UD materials. UD again means unidirectional, so all of your fibers would be in one direction, most likely in the 0-degree direction. So these are very important materials. They are usually produced in the form of round rods, like we can see here down in this picture. They're very, very strong in this actual direction here, in the direction the fibers are oriented, but they're very, very weak in the transverse direction, which obviously makes gripping very, very challenging. Like the same problem, or even harder to do, like with a normal coupon, you might break them while you're gripping already, or you initiate damage to them. So it's really, really challenging gripping these and then getting a good failure somewhere outside of that gripping location. So what can you do? Usually you can use a very, very long gripping length, so you make sure you grip as much as possible, and then also using something like a semicircular grip profile that matches the specimen diameter very, very closely, so that you really kind of like have a snug grip on there, but not too much, obviously, at the same time. And you just want to make sure you match this as good as possible and use a lot of length. Now, these standards here, if we're looking at the EN, for example, the 2561 would be testing parallel to the fiber direction, 97 would be testing perpendicular to the fiber direction. So the EN standards kind of split this up. D3039 doesn't really do that in the ISOs. For example, the ISO 527-4 it also has recently introduced a new test specimen, the type 4 specimen, which has a tapered geometry, which is very uncommon. All of these are usually like you can see here, there's no tapering here. They have the same cross section all the way through, which makes it hard to get that failure in the gauge section where you want it, where you also most likely measure your strain. So now in the ISO standard, there is a new type of specimen where we're trying to get that geometry reduced here in the gauge section. And it's supposed to be used without end taps. And then in the -5, that covers more unidirectional materials, not suitable for multidirectional materials. But both of these use the general principles of the -1. And then quickly on the D3039, it's the most popular standards in North America that I can see for tensile testing of coupons. All of these standards, they're very similar specimens. They're looking for the same results, more or less. And all of them have some kind of recommendation of load string alignment, which is also a topic we're going to cover today. And what should you look out for in general here? I mean, system alignment is very important. We'll cover that. Coupon fiber alignment, so actually making a composite, obviously you need to make sure your fibers are aligned properly in there. Damage from machining, you need to avoid as much as possible, and the gripping pressure must be appropriate to prevent damage. And I usually, when I test composite coupons, then I always try to go as low as possible without at the same time have my specimen slip when I do in-plane tensile testing. Now we're going to move on to compression testing. There's different ways of doing compression testing. The first one we're going to look at here is the end loading. So there's a couple different standards that cover this. The ASTM D695 or the 6484 would be good examples. So what are actually being done here? So if we think of our specimen here being represented by the black part here in the illustration, we're going to have some kind of guidance here, so in form of a testing jig like this fixture that we see here. But really the point here with the end loading is that the force is being introduced to the specimen on the very end. So you're going to have, for example, here, the specimen is going to rest on the bottom here of this block. It's going to be guided here for most of the section. And then at the very end, it's going to stick out a little bit here. And then you're going to come down with a compression platen and you're going to compress it. And that way, your specimen is being held in place by the guides, and then you're introducing the load purely on the ends of the specimen. It can also be done with tapped specimens, as you see here. And then there's different jigs that you can use for this. And this is a very popular one from the ASTM D695, which is actually a plastic standard, which has been amended over time to also include a little bit on composites. It's also being used in an old SACMA standard, or also allowed to be used in the ISO 14126. You can use tapped specimens to determine the strength of your material. You can use untapped specimens to determine the modulus of your material. And then another example for end loading would be the ASTM D6484 fixture, which is for open hole compression. And this can be done with untapped specimen. It can also be used in shear loading, but we're covering here the end loading right now. So this fixture here, you can see you have the fixture, and then you have matching plates here for the fixture to give it nice support. And then you're going to come down with compression platens. So you're going to end load your fixture itself, and then also the fixture is going to transfer those forces onto the specimen on the very ends, and it's going to be supported here in the in most of for most part of the specimen. So these are examples for end loading compression testing. Now we're going to move on to shear loading with an unsupported gauge section. Now, how does that work? What's the difference here? So you're going to have something like a tapped specimen here. You're going to have a clamping force. So you're going to clamp on just like we did, similar to the tensile testing. Could be one way of doing it. You can also use fixtures. And then you're going to compress whatever you're using there. If you're using tensile grips, for example, for this Airbus standard here, or you use something like a fixture for the ASTM 3410 here. So this is the Italy fixture here. You can see you have some guiding posts in there. And then your specimen is going to be in between here, and you can kind of see here the unsupported gauge section. So most of the specimen is supported here within the fixture, and then you have an unsupported gauge section, which is also where you want your failure to happen when you compress this. So you would load your specimen in here. It's basically like this fixture is basically like inverted wedge grips if I'm looking at it. It's very heavy, very big fixture, but you can have pure shear loading. And end loading is absolutely not allowed with this testing standards. It's going to be pure shear loading. So it's going to be clamped on here within there, like you would do with wedge grips. And then you actually on your testing machine would put this in between compression platens. So you're end loading the fixture, but then the fixture will transfer those forces via shear onto your testing coupon. Other ways of doing this would be example of the Airbus standard that you can see here, where you're using wedge grips, and then you're clamping onto your specimen, and then you drive those wedge grips into each other to initiate compressive forces, which then are being transferred into your coupon again via shear. So the Airbus standard here is a good example. A little bit special here. I've found what they found in the Airbus standard. There have been revisions over the years, and actually, so you're using something like a wedge grip, right? So you're going to have jaw faces here, but instead of clamping onto your specimen directly with the jaw faces, you're using something like a load introduction plate, which you can see indicated here in the illustration. You can also see it here on the picture. So this load introduction plate is sticking out above or beyond the jaw face, like jaw face ends here. The load introduction plate will be beyond that, and this really helped to on the one side get the failure in the right in the unsupported gauge section here, where you're actually also measuring your strain, and at the same time it also helped Airbus to not have failures if you do something like combined loading, for example, to have the ends crush. So they get much higher forces out of this, and they also get the failure where they want it with this. So if you're doing the Airbus standard, you can do this with you can determine the strength of plain, open hole, or filled hole compression composite specimens. Again, you can do shear or combined loading, and pure end loading is the only thing that is not allowed in this ASTM standard. And in the revision now, it's actually mandatory if you're doing the pure shear loading to use the force, the load introduction plates here. So that is mandatory now. And then looking at the ISO, this one really allows any fixture that meets the bending requirements that are written out in the standard, which is the 10% bending limit. The force can be introduced by shear, end loading, or combined loading, and all kinds of fixtures are allowed. For example, the ASTM D695 jig we looked at in the previous slide, you can use the iterary fixture, you can use something like the Celanese fixture. So there's really many different fixtures that can be used with the ISO standard as long as you meet the bending requirements. Now moving on to the last compression, in-plane compression testing way of doing this is combined loading unsupported gauge section. So how does that look? Well, we're going to clamp onto our specimen, and then we're also going to load it on the ends, and then everything is going to be compressed together. So we're introducing our compressive forces here via shear and also via the ends. This would be the testing fixture. This is how the testing fixture looks like. This here is illustrating the fixture before it's put together with the specimen, which would be here on the photo. This is how it looks together. This is how it looks while you're loading your specimen. So you're going to have the different blocks here that are supporting your specimen. They're guided again, just like we saw with the iterary fixture, because again, alignment is very important. And then you're going to have the specimen here either stick at the ends, or you're going to have plates there to transfer the force. And then you're also doing the shear force here onto your specimen with the bolt. So your bolt is together, and then you need to have a good combination of, making sure that you load it on the ends, but also torque enough to introduce some shear load, because you want to test combined. And then your gauge section here will be free, and that's also where you want your failure. So there's two different procedures here. You can use untapped specimens, which is the procedure A, and you can use tapped specimen, which would be procedure B. It's really depending on what is required. What do we want to test here? And then one requirement of a successful test for this testing method is that the ends, because we're also end loading, right? So you don't want those ends to not crush during the test. Otherwise, it's not going to be a valid test. Okay, now moving on to the next slide here, in-plane shear. And we're going to move kind of in terms of complexity in regards to the specimens and the fixturing and the procedure itself. So we're going to move in complexity from the left to the right here. So looking at in-plane shear, what can be done here to test that kind of characteristic of your material? So in the most, or the simplest way of doing it would be the in-plane shear testing here of a coupon that has the fiber orientation of plus and minus 45 degrees. So you don't have any fibers oriented in the 0 or the 90 direction. You're only using 45-degree plus and minus. And then you can see here how the failure looks. I mean, that really looks like this got sheared apart, right? So what are you doing? You're making a coupon like this, and then you clamp onto it with wedge grips, and then you're pulling it apart, and you can, measure different strains here with, for example, clip-on extensometers. ASTM D3518 would be a good example, which is using this principle, which is basically in accordance to D3039 that we looked at in the in-plane tensile. So it's going to be the same procedure there. It's just a different coupon that you're using, different layout, different orientations of the fibers. Now, this is not pure shear stress, though. There's going to be a portion of actual tension force. So you got to be careful using these results for your design data, because, you know, you can try to calculate out that actual force, but really, you know, you have a very, very complicated strain field here with many different forces. So it's not pure shear. Something that's a little bit more towards pure shear would be the ASTM-D 4255. It uses a rectangular specimen, which is clamped between rails, like you can see here. Now, for the 4255, there's two different procedures. There's a 2-rail and a 3-rail fixture. Both fixtures can be used in tension and in compression. And you would use a laminate of balanced and symmetric construction with the 0-degree fibers oriented either parallel or perpendicular to the fixture rails here. So this is a little bit better than the in-plane shear that we looked at before, but still the next two that we're going to look at, the D5379 and the D7078, produce superior shear responses versus this 4255 standard. Another disadvantage here also, as we're moving up in complexity, this specimen actually needs to have 6 holes drilled into it. So you're going to have here the bolts that you actually use to connect your rectangular specimen to your fixture. But drilling holes in composites is not made very easy, and it's also a risk of damaging the specimen. So a lot more specimen preparation compared to the simple coupon that we're using here. The same is true for the V-notch. Now, instead of holes here, you got to make a actual notch in your specimen here on both sides, which can also be very, very challenging with composite materials. Now, the advantage, though, is this is true shear strength and modulus. But yeah, of course, it's at the loss of a very complex specimen, and also, you know, a little bit more difficult, obviously, to get this correctly in the jig, loading it and all that. The whole procedure is going to be a little bit more complicated. Can be done tapped and untapped, pure shear in the notched area of the specimen, and the load is being introduced through the top here, and then, you know, this part of the fixture is being unsupported for the 5379. For the 7078, you're going to load this in tension, and then the rail introduces shear forces into your specimen through the specimen faces. It's a large gauge section, so if we compare these two specimens here, the D7078 is going to have a larger section there, and gripping method. This allows you without the needs for holes. So you have bolts here too, but they're actually not going through the specimen. So compared to this 4255, you don't have to drill holes. The bolts are there to clamp onto the specimen to make sure to hold it in place. And now, as the last example for the in-plane shear, we got the ISO 20337. So this is pure shear loading. This also allows you to test specimens that would exhibit very, very large shear strains above 5% and beyond, which is a limitation of these other standards. So if you have those large shear strains, this is probably the method that you would want. It's also much more reproducible. It's a much more reproducible test procedure because the maximum shear stress occurs in a central portion of the test specimen, and this procedure also avoids invalid tests due to material failure of the specimen at the edges where you're gripping it, for example. So it's a much more reproducible result that you're getting. You can do those large shear strains, but again, it's a very expensive, very complicated specimen design, and it's also a complex fixture and procedure. So it's not very easily done. Now moving on to interlaminar shear testing. Now we got the short beam shear here. There's various examples for that. So you can use supports here, very, very narrow, very close to each other. And then you have that anvil coming down. You have that small, you can see here in like yellow oranges, the specimen coming down. So this is a parent ILSS strength only. You can't really do modulus determination with this. It's a very simple specimen though, and this is widely used for quality control on the materials. But you can see here in the force diagram here, there's going to be some bending stresses initiated in the specimen as well. Now, if you're doing something like a double beam shear, for example, the ISO 19927, this is true interlaminar shear strength and modulus. And again, using a rectangular specimen, it's obviously just a little bit longer. And if you look at the diagram here, you're going to have a state of pure shear stress where your bending stress is 0. So you can get the true interlaminar shear strength and modulus at those points in your specimen. You can kind of see the failure here in the specimen. I hope that is visible to you there. That's how that would look if you have an interlaminar shear failure there. And then you can also do this with the V-notched shear of the D5379. Again, complex specimen compared to the other two, obviously. But you can use this to establish your materials design data. And you can see again here in the diagram, within the notch, you have pure shear where your bending stresses are 0. So you can get this. It's a small area, but you get pure shear stresses. And this is what it would look like if you're capturing this with, for example, digital image correlation. Okay, now moving on from the shear testing to flexure testing. Many different standards cover this. It's basically, you measure your materials, you subject them to simple beam loading. The ratio and of lengths of the specimen to thickness is large to minimize shear stresses, because now we want to find out about the flexural properties of your specimens. And you can do this with different types of loading. You can use either 3-point or 4-point bending. So 3-point we saw there with the short beam shear. 4-point bending would be something like this here. So you have 2 supports on the bottom, you have 2 anvils coming down. And this is what a typical testing curve would look like if you're putting the stress over the strain. This would be a typical curve for a flex test, and you can determine your modulus here on the curve. Now, going into the through thickness direction here in tensile or compression with a direct method. So specimens are being cut out of thick laminates, and this way of testing allows you to determine the modulus and the Poisson's ratio, as well as the strength. Now, if you need to determine your modulus and Poisson's ratio, you will have to use strain gauges for this, because the specimens are pretty small. Like, you won't really be able to attach something like an extensometer on there. So how does this work? So you're going to have these studs here, which, on this side here, they match the profile of your specimen. And then you have an interface here that you can connect to your testing machine, and then you're pulling on it. So you're pulling on the top and on the bottom here. You have your stud. You're going to add an adhesive to that, to the stud. And then you actually glue your specimens into that fixturing. So you're going to probably have a couple of those ready, and then you start testing them. So a lot of preparation needed there. You actually have to glue your specimens in, kind of like how that can look. So you can see it's very, very small. You have small specimens from thick laminates that you're testing there. And how could that look in compression? This is how that would be with between the platens. You got your specimen here in between, and the strain gauge is attached to it to get your modulus and your Poisson's ratio, or at least do the measurements to calculate those. There's also an indirect method of doing this. Examples for this would be the Airbus standard 1-0069 or the ASTM 6415. This is a curved beam indirect method. This is how it would look like if you're looking at a picture of the actual fixture and the specimen in between. So you have your flat specimen, but it has this curved shape. So it's already, it's a special specimen, right? Again, this is not very easily done. So you need that specimen, you need that jig, and then you initiate forces here. You're going to compress this, and then what's going to happen here in the corner is you're going to get a state of tension stress in the corner. Now, this is the indirect method. You're only going to get the strength. You're not going to be able to determine any modulus there, because even strain gauges here attaching those is not really done. And yeah, it's very suitable for thin laminates. Another way of testing that needs to be done, we've touched on this real quick, was interlaminar fracture toughness. So there's different modes of doing this. There's the tensile opening in the mode 1, you got in-plane shear mode 2, and then you have anti-plane shear in the mode 3. So there's different modes that you can test to, different ways of stressing your specimens. Most popular for the G1C testing here, from what I can see, is the ASTM D5528. We see that to be the most popular one. There's different other versions. We got Airbus, ISO, and EN also with different examples. And then you have something like end-notched fracture here, the G11C. Different examples down here. I mean, the G1C is probably the most popular from what I've seen. You just real quick here on this one. So you're gonna have arms of your specimen here. You're gonna have an insert in there to simulate a delamination in there when you bond these two together. And then you're gonna start pulling them apart. And at the end of your insert, that's gonna be the starting point of your crack. And then there's different loading cycles. You're gonna first initiate a crack and grow it for a certain distance, and you're gonna unload, and then you're gonna reload the specimen. And then as the crack grows through there for about 30 millimeters, you're gonna take different you're going to capture the data at different increments on the specimen. So very, very complex testing, also very low forces that you're going to see here. I mean, the ones that I've done are around 100 newtons. So comparing that to like some of the in-plane and compression testing that we've seen, where you're like, you know, much higher loads in the kilonewtons range, maybe even over 100 kilonewtons. This is going to be 100 newtons. So it's going to be 1/1000th of that. So much lower loads here in these tests. Another test that needs to be done, we've touched on this before, is the bearing load. So you're going to have a hole in your specimen, and then you're going to insert a steel pin here or a bolt, and then you're going to put this together with the support plates. You can do an averaging extensometer on both sides to average your bearing strain, and then you're going to pull on this, and then you can get your bearing strength, which is not a material property. It will change depending on the size of your hole in there. So if you're using different fasteners, different hole diameters, you're going to have to do a lot more testing for each of those, each of the different combinations there. And you can see a couple typical failures down here in the pictures below the loading curve here. And now lastly, on the testing examples that we're going to show, we're going to look at compression after impact testing. So you're going to have an impact location on your plate. This is usually been done on rectangular plates, and you know, you might have a visible damage on your surface, but you might not have. Like if you don't see it visibly, that doesn't mean that some of the matrix might be cracked down here, or maybe even some of your fibers broke. So just because it was impacted and you don't see something on the outside doesn't mean there is not any damage on the inside. So this needs to be simulated. How do you do that? So you can see here the testing plate being held in place, and then this is supposed to be the weight coming down the impactor. It's going to have a weight on the top somewhere. So if you look at the drop tower here, you're going to have a known weight. You're going to impact your little plate down here with that, and then you're going to know the force that this has been impacted in, and then you take that piece of plate, and then you're going to put it in another testing fixture. You can see some examples here from ASTM or from Airbus. Obviously, Airbus is going to be interested in this compression after impact testing, because, you know, this is usually done to simulate something striking an airplane. So if, unfortunately, for example, birds get hit by airplanes, or you have somebody trying to do repairs or inspecting the airplane, and then there might be a tool being dropped on the airplane wing or something like that, we've got to make sure that those materials, even after they have been impacted by a certain amount of force, that they can still operate in their normal environment. So the normal stresses that they exhibit during starting, landing, and flying through the air, we got to make sure that there's enough strength left for them to keep operating. So you put you impact the plate, you put it in your testing jig, and then you're going to compress it, and you're going to find out how much strength is actually left in my material. So you can do this on a tensile tester. Like here you have, you know, in this setup, we got an environmental chamber. So our grips are being extended into the chamber, and then onto the grips we have compression platens mounted, a spherical one on the top, a fixed one on the bottom. We put our fixture in between, and then we're going to compress this this specimen in the fixture and find out about the force that are left in there. Now, moving on a little bit to testing challenges. There's a few ones that we're going to look at: alignment, strain measurement, testing environment, and so on. So we're going to start with alignment. Already mentioned this a few times. What do we actually mean? Well, this would be what good alignment looks like. What would be bad alignment? Something like a concentric arrow that we can see down here. So if you have your grips offset to each other in any kind of, you know, in any kind of direction, you would have to correct for that. Otherwise, you're going to pull your specimen not straight, right? You would pull it in some weird S shape kind of here, or you could have something like an angular arrow where your grips are not straight in that regard, and that also kind of puts unwanted bending strains on your specimen when you're testing. So why is this even important? If you think of a normal metals test here, and you pull it kind of, you know, at an angle here, you're gonna have a misalignment, right? So there's an uneven stress distribution, and the metal will yield here at this site here where you know you're at any high stress region, and it's going to start yielding. But metals yield quite a bit, right? It doesn't mean that just we got them beyond the yield point that they won't carry any load, right? You can see here on the load curve there's actually a lot of strain before that actually breaks. So the stress will just redistribute, and the effects of the misalignment will not be as strong as on your test results compared to a composite. So if we think about the same example here with a composite, you're going to have a misalignment, uneven stress distribution. You're going to pull much more here. Fibers in this region here, they can only strain so much, only a few percent usually. If you have a unidirectional material, it's going to be like, 1, 2, 3% of strain. And then the fibers are just going to break in this region, which then transfers the forces on the rest of the fibers, which then also will be overloaded pretty quickly, and you're going to have a rapid failure. And the effect on your test results is actually pretty significant. So if I test on a tester that is not perfectly aligned, doesn't use the correct type of grips, I can have 10%, but even up to 20% differences in the max strength of my material. So it's really, really dramatic differences there if you have misalignment. So how can we fight that? So you need a testing machine with high axial and lateral stiffness, needs to be guided. Our machines have guiding posts next to their ball screws to take care of that. You need a thick crosshead, and you also need something, depending on your setup, like an alignment fixture that you can see here between the crosshead of the machine and the big load cell here of your machine. You have your alignment fixture, which you can then make adjustments to the concentric and angularity arrows. The other thing that's very important here is the gripping technique. You want to use a good grip that is symmetrical. So if we look at this grip here, on the right and on the left side, it's perfectly symmetrical. It also uses a moving body design. You can see that here in this animation, like the whole grip body is pulling down, and that moves through the wedge geometry, moves the faces together completely on the horizontal axis. So there's no actual closing of your jaw faces. They only close on the horizontal, which is much better to introduce the loads to your coupon. So you got to make sure you got that moving body design. You got to make sure you have the right jaw faces, and then you need to make sure that also you use specimen stops, which I'm going to show you here in the video. So this is this would be a specimen stop. You install this on your jaw face. You can adjust it depending on the width of your specimen, and you want to set this up so that your coupon now, as you can see when you're loading it, that your coupon is perfectly centered in your grip, in your jaw faces, and that will really help you to have much more reproducible testing to make sure that, like, because what's the point, right? If you align your whole load string, but then you don't load your specimen at the right angles, you're going to have a misalignment anyway. So make sure that you use specimen stops for your coupon testing. Much better reproducibility. Now, how do you verify alignment? There's different ways of doing this. NatCap, a lot of you probably have to follow the NatCap requirements, and one of those, is a lot under NatCap, but one of those that obviously we as a testing machine producer care a lot about is the alignment of the testing load string. So there's different strain gauged specimens. So there's multiple strain gauges on these specimens, depending on what standard you're following here. They look kind of like this here if they're enclosed. So you use that, and then you pull on it, and then in your load string, it will show you, at least in, with our software, for example, our Line Pro software, it will show you the angularity or the concentric arrow, and then it will tell you, okay, you got to turn this screw on your Align Pro. There's multiple screws on there to make adjustments, and then you can reduce that bending arrow, and then you can get it within the required limits. Compression testing also requires good alignment. So a couple of things that we can look at here. We have compression platens. The upper platen usually should have a spherical seat, which can be locked in position. You need to have a hard surface, and you need to make sure that you have alignment rings so that you can center your specimen nicely in between your compression platens. The spherical seat, what you would do is you unlock all those screws here so that your spherical seat is free and movable. And then you drive your platens into each other and bring them up to the force that you're expecting your brakes at. So if you're testing at 50 kilonewtons, you know your specimens break at that. You would want to put your platens together to at least 50 kilonewtons, and then you tighten down these screws here again, and you can remove the load, get your platens apart again, and then they should be perfectly parallel. Guided fixtures obviously is the other thing. Like if we look at the ASTM D3410 again, like making sure that they have guiding posts, they're machined very, very precisely, and then the grips obviously, and then you can verify this with strain gauged specimens again. So also for compression alignment, very, very important. And then again, why is this so important? Well, let's just look at some results. These are the results of 6 specimens here tested with poor alignment, and these are the results for good alignment. And you can see, like, just the tensile strain, for example, you have some here that have already their failure between 1.1 and 1.2, whereas the good alignment, you don't have anything that really breaks before 1.3. So you get a lot more strain, which also means you did not strain these specimens here until what they could really strain to. Right, and you also probably don't get the loads high enough. Like all of these are basically breaking over 2000 megapascal, whereas some of these are clearly below or just at 2000 megapascal. So a lot more data scatter, a lot more variability. Same is true for your modulus determination and all. You're going to have a much greater mean value if you test with poor alignment. And then at the same time, NetCap just requires this. So if you need to conform to NetCap, you got to make sure that you're within those bending requirements, which for static composite testing, which we're talking about today, is 8%. So we have that white paper, which I think Martha has shared already with you, where you can look at these differences and why alignment is so important. Strain measurement, going to look at that here quick. So strain gauges are very commonly used in composite testing. In some cases, it's even there's no solution for an extensometer, for example. In other cases, the test specifications mandate the use of strain gauges. You can use these in different directions to get your strain reading. You can use multiple to average, or to get the difference in the actual strain, the bending or the shear strain transfers. You can bond these onto your specimens, which again, these are consumables, right? So again, a lot of preparation needed here. You need to make sure that they're oriented in the correct way. You don't want them, again, to be misaligned, the strain gauge on your specimen, right? And then you need to bond it, and then you break your specimen, and then you have to start over with the new specimen. So there's a lot of work that needs to be done to use these, right? So you might want to consider something like a contacting extensometer, so normal actual extensometer, different gauge lengths, different travel limits, and then there's also biaxial clip-on extensometers that can be used to average your strain, or also maybe to measure the strain in the transverse direction and then in the actual direction, and you can determine your Poisson's ratio. But really, if we look at those videos earlier, like extensometers are going to have a rough day, right? If we have those explosive failures, so they're eventually going to be damaged or even completely broken if you test over and over and over, and they just get impacted by all those high energy releases there. So video is really the way to go as long as the video extensometer meets the accuracy requirements of the standard. And the other advantage here, obviously, this is your operators don't need to attach anything manually. That is obviously a great advantage there. And then on the other side, also, it's going to be much more reproducible. And on top of that, you can use something like digital image correlation, which is very popular in research and development. So non-continuous video extensometer, got to make sure, like, we do have the accuracy to meet the ISO standard, for example. There is an LED light supporting an fan to prevent environmental influences. And yeah, again, it doesn't require your operator to attach the extensometer, which reduces the influence of different operators and increases your consistency. Can also be used with chambers. So you can see one here mounted in front of a chamber door. So that's obviously very, very nice to do too. Digital image correlation. This is an example for open hole tension testing. So you can make these fields here. It's like a certain frequency you can set up, taking these measurements with specimens with a speckled pattern, and then the digital image correlation kind of as the speckled patterns move, you can simulate the strain, so you can put digital strain gauges on your specimens in different sizes, different orientations. So very, very nice, but getting that into the standards is probably, if it's ever going to happen, it's probably going to take a while still. So this is mostly used for research and development. Really quick here on testing environment. So there's normal testing chambers that we, for example, supply, which, you can have them with electrical heating, just like a normal oven, right? You're going to have heating elements and you're going to force air over them to heat up. And then there's different ways of cooling down. You can use something like liquid nitrogen or CO2. It can get down to minus 150 Celsius with that. Anything below that, you really need some specialized chambers. And then also humidity chambers should be used to simulate those different humidities. We talked about this earlier in the presentation. So you need to make sure that you condition your specimens in the right humidity environments that you're trying to simulate. And then also for the correct time until they're saturated and took up that moisture. Now, managing large numbers of test types and standards. So software needs to be powerful. Our Blue Hill Universal software, for example, we have a composite module in there with all these kinds of different testing standards that we talked about. Most of them are included in our module, so you already have the testing methods set up. So your test frame is already configured in terms of how fast to go, what to measure, and all these different things that need to be set up in there. Range of different standards that can be covered. And also you want to make sure that your software is pretty flexible, easy to use, and obviously you can create new tests or modify the existing ones. It can be used on a touch screen. You can export your data in various ways. And then one thing that is often overlooked is this really gives you access and control traceability option. So you can we already have revision history now. In every new version of our software, there's revision history. So if anything ever changes in a testing method, which could be a nightmare, right? If somebody just either on purpose or on accident changed the testing speed, you might not follow this testing standard correctly anymore. So revision history would show you that. But to even be able to prevent that, you can have something like the traceability option that we're offering with sign-offs. So you can have different security levels, and your operators, for example, the testing operators, you could prevent them from being able to make changes to any testing method. And if they would attempt to do so, or if somebody else like the lab manager tries to do so, and you have some other manager above that, you could have sign-offs in place where you make sure that somebody reviews that, sees the different changes, and then either approves them or not. And then also those testing methods would not be able to be used until they're approved. So that's how you can entirely prevent that. And then also this helps you a lot with your audit trail for NatCap. So very powerful software there that you can use, and really, all that manual work with the different in regards to the testing can be captured then with the traceability option. A little bit on productivity here. So you see here, like if we're looking at our normal system, how do you get that productivity? Well, first of all, you got to make sure you got your alignment correct. Then you use something like a load cell. Our load cells can be calibrated up to a range of 1 to 1,000. So a 300 kilonewton load cell, you can take tests down to 300 newtons. You're still going to be like at and above 300 newtons. You're still going to be in the calibrated range. So that's very powerful if you do many different tests where also some of them might have much lower forces. And then, of course, you're also going to be able to piggyback on those grips. So if you need even smaller load cells, you can piggyback those. You can add temperature chambers and you have your grips here precision aligned. You can add the compression platens like we looked at, and then you can test your D695 or your compression after impact in between there. And the same is true. Not going to go over all these here now. We're getting a little bit short here on time, but the same is true for hydraulic grips, extended hydraulic grips going into the chamber. You can see all these different examples. Most of these we actually talked about today. Most of these fixtures can then be used in a chamber. You're going to piggyback compression platens on your grips and then put those compression or flex shear fixtures, whatever it is, in between there and do your test at temperature without having to remove your grips, which would sacrifice your alignment, right? So you don't want to do that. You want to keep your grips in place. So piggybacking on top of them is really the way to go. A little bit on future trends real quick here. So applications, green energy, wind, hydrogen, that's going to pick up. Hydrogen tanks being made out of composites. High volume for automotive. So the adoption rate in automotive is still pretty low. We really need that high volume production there, which which can be done, for example, if we move more towards thermoplastic materials for our matrix, maybe that can mean that we can get similar production rates to injection molding, which would be for like the plastic process versus doing the autoclave process where you actually need to cure. Recycling is a big trend. I mean, there's almost no every few weeks I feel like there's something in composite world where somebody is recycling materials through thickness reinforcement. So you're going to go 3D with your fiber orientations. Generic material specifications might be something that we're going to see in the future where you have grades of composites. Right now, it's really like to each manufacturer, and there's no like general grades that you can buy. It's really depending on each manufacturer. Same then 3D printing. We're already doing additive processing more or less, more automation in the manufacturing, and then for the testing, probably going to do more modeling versus less testing. Maybe, who knows? We'll see, right? Okay, so with that, I thank you for listening. If you have any questions, we can try to cover a few now. I know we're a little bit late on time, but thank you for listening. And yeah, if you need to get in touch with us, you can get in touch over our website, obviously, or you can contact me. So thank you for listening. And Martha, if there's any questions, please let me know. We can try to go over a few.
Yeah, thank you. That's great. So we do have quite a few questions that come in. I think we'll be able to get through a couple. I'll make sure that Stefan receives all of the questions and he can reach out to everybody that we didn't get to and make sure that you guys get your answers. First question, I see now somebody has asked, right now they only test to ASTM D3039. In the future, they might need to test additional testing standards. How can they kind of start preparing for that now?
Yeah, that's a good question. I mean, really, like you got to make sure that like the testing machine, like if you don't even have one yet, you got to make sure that you have enough test space in between there for different fixtures you might use. If you know that you need to test that temperature, obviously you want to make sure that you already have a testing chamber in place. And really, I mean, you need a modular system where you can make adjustments like you've seen here in my presentation. You can mount things to your grips, you can do different connection types there, and then if you're just doing tensile right now, and then in the future you might have to connect something actually like a DCB test that we've seen at a fracture toughness test. You can do that with the different interfaces that you can put onto your grips, for example. So yeah, just basically the machine needs to be capable of so before you purchase a machine, make sure that is possible. Like, how modular is the system really? And then also, again, software is sometimes underestimated. Making sure that the software is capable of doing many different types of testing. And then we, for example, offer something like Test Profiler, where you can really have many different loading cycles, if that ever becomes of interest.
Yeah, similarly, someone has asked, and this probably overlaps here, how can they improve productivity when frequently needing to change the testing setup? Okay,
yeah. So that is pretty common in composite testing, changing the test setup, right? So yeah, again, you can think of it different ways. So you could consider getting even a second frame to do certain testing on there, right? If it's depending on the number of specimens that you need to run. So you could have a second test frame that you use, but really you gotta make sure that you have all your setups correctly, that you have the load cell, for example, being without having to switch the load cell, without having to piggyback one. Those are great advantages. And there's also really things, this is very popular, for example, in the metals industry too, where you have completely automated systems where you have a robot basically loading the specimens. There's going to be some like different racks with different, like all the different specimens that need to get tested in there, and the robot grabs it, puts it into your testing machine, and everything runs automatically. That's really like high throughput. I would say an automation system is probably kind of like the top-notch solution there.
And then last question, and we'll make sure we get the rest of these over to you. Similar to CAI, are there any standards for tensile after impact?
Tensile after impact. That's a good question. I mean, I'm not really aware of any. It's also usually, I mean, there's some trends now that I've seen in the industry where like some people claim, oh, with this combination of matrix and fiber, we get close to or even the same strength in tensile as we get in compression, because that is pretty uncommon. Usually, if you have a coupon, like a unidirectional coupon, it will be stronger in tensile than it is in compression. So compression is really like what there's so many different standards there, right? So compression is really, that is the weak link in that direction. So I think compression after impact is probably mostly done in compression because of that. Like you're going to pre-damage your coupon, and it's going to be able to withstand a higher load in tensile than it is in compared to compression testing.
Great. Well, thank you very much, Stefan. We really appreciate you being on. I know that Instron is going to have a booth at CAMX next month in Atlanta, so I hope you guys will all stop by and say hi to them there. We will make sure that we get the recording, the slide deck, and the white paper and everything distributed to all of our attendees tomorrow afternoon. And then we will have a brief survey that pops up on your screen at the end of today's webinar. We'll hope you'll give us a little bit of feedback, and you can also drop in your contact information there if you have additional questions and you'd like somebody from Instron to reach out to you. Anything else for us today, Stefan?
No, yeah, it would be great to see some of you at CAMX, and thank you for listening.
Great. Have a good afternoon, everyone. Thank you.